right, I'm gonna let y'all get started on the warm-up problem. It should look pretty similar to something from your exercise. So here are, did it? Hang on, I ruined it. Shush, pretend you're not watching this. Pretend that didn't just happen. Okay, so here are two separate sorts, and I have various stages within the sorting algorithm. They are in the appropriate time order. They may not be sequential. And so if you look at the sorts, you've learned three so far: selection, insertion, and merge. Try to determine, if you didn't read what I put on the screen, which sort is which based on the order in which they are approaching a sorted list. Go ahead, take, let's say, 3 minutes, and then we'll talk about it afterwards and how you can do these. I think you have something just like this on your exercise. All right, let's chat about it and how to do these types of problems. So let's start with sort number one. So before maybe we dive too deep into it, let's remind ourselves, we've learned three sorting algorithms so far. What are sort of the key defining characteristics of the sorts? So remember that with insertion sort, what we're doing is as we loop over the unsorted list of items, every time we encounter something on the boundary of the unsorted and sorted lists, we take that item and then we place it where in the currently sorted list it belongs. So in insertion sort, you can't stop early because the sorted list is all sorted relative to itself, but we don't know if that's necessarily like the most sorted order for the entire thing. We're just kind of growing the sortedness in relation to itself, and then the whole thing is sorted once the sorted list expands over the unsorted list. Selection sort, that's one where it's not necessarily thinking about sorting in relation to each other in the sorted list. It's more like, okay, now that we've gotten to this position, let's loop through the unsorted stuff, find the thing that belongs in this position, then we select it and pick it up and drop it in. So selection sort, you can stop early if you only need the top K sorted items. And then merge sort is that one where we take everything and we divide and conquer, where we break it down and break it down and break it down until we get to lists of one. We mark those lists of one as sorted, and then we take the two lists of one and we combine them into a sorted list of two. And then as we continue to unroll the recursion, we take two lists of two and we combine them into a sorted list of four. And so a kind of pairwise sorted list grows in that manner. So if we look at sort number one, here it starts in unsorted order. And then if we look down here, the next thing that happens is we see the 11 that was previously here is swapped with the 23 that was originally at index 0. And then if we look down here, we see the 23 that was previously swapped over here has now found its way to index 1, and the 37 that was over here got swapped over here. So does anyone want to tell me what they think sort number 1 represents? What does sort number 1 represent? Yes, please. I agree. Selection sort, and I think you're absolutely right for the reason. If you see the absolute smallest thing in the entire list in like the very first steps immediately pop to index 0, well, that's selection sort, because that means I looked through the entire unsorted list, found the smallest item, and swapped it with whatever was at index 0. And then I looked through the unsorted list and I found the second smallest item, and I swapped it with whatever's at index 1, so on and so forth. Any questions on how I figured that out for sort number 1? Or any questions about sort number 1? Okay, sort number 2 is harder. I didn't talk through how merge sort works in terms of the ordering of things. I just kind of showed you the theoretical of it. But does anybody have any guesses as to what we think sort number 2 is, or anything they observe in sort number 2 that might give them a hint as to which one it is? Yeah.
The only difference in the first step is that 12 and 18 swap.
Mm-hmm.
That could possibly indicate insertion order.
That's true. Yeah, they swapped, because you're right. A lot of insertion, like there was that, I always think of insertion in the like algorithmics, like they're doing that little clap thing, like they're sort of swapping down until they get there. So it does look that way. That's true. Anybody see anything else happening in sort 2? Any other sort of clues pop out at you? No? So we notice our friend's correct. The only difference between this step and this step is that 12 and 18 are swapped, which is appropriate. That then sort of puts 12 and 18 into relative sorted order to each other. Yes, please. Sure. Yes. Absolutely. Absolutely correct. Yes. So sort number 2 is technically merge sort because it does follow in this sort of pairwise. It's sort of like we divide it into all of these subdivision arrays, and then we sort the arrays in relation to each other until we eventually get down to, here we sort of have, I think we eventually have like, this is a sorted list down here, but none of this is sorted. And so it's like, it's sort of growing pairwise to the left. Like I said, I didn't talk to you about how that works within merge sort, but I think this will, oh God, okay. That's the one thing I don't like about Visualgo. It really wants you to take that tutorial. Let's watch merge sort on Visualgo. I think it makes it a little clearer. So let's see. So let's say we have a sorted list. So we sort the first 2 items. That's like the base case. And now we're sorting 2 lists of size 4 together. There we go. We're sorting that 2. That's a base case. Now we're combining this set of lists until the first half becomes totally sorted.
Now it's time to deal with the back half. So there's a base case 2-item list of items size 2. Since there's an odd number, that becomes a list of size 3. Here we sort the back half. Now we're going to sort that entire back half together. And now the final stage before the very final interweaving is sorting these 2 lists that are each half the size together by interweaving. And then we get a sorted list. Any questions on merge sort there? Cool. Okay. Great. So then, yes, this sort 1 is selection sort. Sort 2 is merge sort. All right, let's talk about the exam. 1 week from today is your final exam. So reminder, we are not doing anything during finals week. I can't tell them to stop doing it. I don't know why, but they keep assigning a time for us on MyUW for finals week for us to take an exam. Don't come to that. There's nothing happening. I won't be here. Nothing's happening during that time. I don't even know what day it gave us or whatever. So your only final is the one that will be taking place a week from today here in class. It is going to follow the exact same format as the midterm, meaning we will have a 1-hour exam. You can bring any amount of notes that you want as long as they're on paper. I don't care if they're typed or handwritten, whatever makes your life easiest. We will take those exams. We are going to grade them as quickly as we can. We will return them to you week 10, and then you'll have a week to resubmit your exams. And then we will take the average of your 2 grades, which is another way of saying you can make up to half of the points missed back on the resub. The final exam will mostly be focused on the topics that we learned weeks 5, 6, 7, and 8 in this class, meaning today is the last day of content that is eligible to appear on the final exam. You still have an exercise that covers the stuff we're going to talk about like next week and so on, so you still get points for it. But for example, we're going to do dynamic programming on Monday. There's no dynamic programming on the final exam. There could be heaps, all of the graph stuff, disjoint sets, sorting algorithms, and then things build on each other, right? So I might give you a scenario, and you need to think from all of the data structures and ADTs we've learned of, which one best fits that scenario. So it is cumulative, but it will be mostly weighted towards things we've learned weeks 5 through 8. Any questions about the exam, logistical or otherwise? Yeah, please. Yes, it will be about the same size length as the midterm. We only have 50 minutes, so it'll be about the same size. Any other questions, concerns? Okay. I know the TAs are hosting a exam review. I should have put it on the slide. I'm pretty sure the exam review will be Wednesday next week, starting at 6 p.m., but I'm sure there's an ed post with more details on that. The TAs managed to get the review recorded this time. We had to do a bunch of fancy stuff. So there will be a recording of the review from Wednesday available for those that want to practice. Any other logistic or administrative questions? Anyone? No, we're all chomping at the bit to learn more sorting algorithms. Of course you are. Yay, sorting algorithms. Okay, so we ended Wednesday talking about merge sort. And we just talked about merge sort there. We saw an animation of it. And the thing to remember about merge sort is that merge sort was that divide and conquer attempt, which means it used recursion. It split apart the problem into small pieces, and then it used a particular algorithm and how to recombine those pieces. In merge sort, what we did is we just split without looking at any of the numbers until we had a list of size 1. And then when we were recombining the lists, that's when we were doing the comparison logic, making sure that we were putting things in sorted order. Can anyone remind me what the worst case runtime of merge sort is? What is the worst case runtime of merge sort? Yes, please. N log n. And if anyone asks you, that is the best worst case scenario of a comparison sort that you can accomplish. As of right now, the fastest worst case scenario of a comparison style sort is n log n. What about the best case scenario of merge sort? Does anyone remember the best case scenario? Yeah, n log n. Merge sort, it does not matter. It will break your stuff apart and recombine it. It does the same thing every single time. It is dependably excellent. That's why it's my Whitney Houston of sort algorithms. She does not miss, okay? We are going to be talking today about something called quicksort, the best branding of any sorting algorithm, frankly, which follows a lot of the same philosophies. It's the same divide and conquer, but instead of just splitting based on size, now we're going to split and use our sorting logic at the split part, and then the recombine part is where there's not really much logic. We're just going to jam things together. So, quicksort. Quicksort, the first thing it does is it is going to look at your collection and it's going to pick something called a pivot. And then it is going to split the rest of your numbers into items before the pivot and items after the pivot. So here we picked the pivot, just whatever is at index 0, and then we will split it into everything that comes before that value, which is 8, so 2, 1, 7, 6, and then everything that comes after it, 91, 22, 55. But notice we haven't sorted those items. We've just split them, and then we know the pivot goes in between those two things. We will continue to pick pivots and split until we eventually get down to lists of size 1. Pardon me. And then when we recombine, we have already done the logic. Pardon, sorry, microphone. The inhumanity. Okay, so when we recombine, that's when everything will theoretically be ordered appropriately. There we go. So, okay, great. So we are going to have to pick this pivot at every level of the recursion. And right now, what we're doing is we're just picking the pivot based on whatever is at the front of each of the subarrays. Pardon me. So we pick 8, it's at index 0. When we split the arrays, we'll pick 2, because that's at index 0 of everything that came before 8. We'll pick 91, because that's at index 0 of everything that came before or after 8, so on and so forth. And we will pick and pick and pick until we get down to items that are of size 1. Damn. Okay. Once we have picked, as you can imagine, once we get down to items of size 1, since we've been swapping them around the pivot, then the recombine stage doesn't need any logic. It's already sorted. We just have to get it back into its original state. There we go. Cool. Okay. I don't cough all day. It waits until I lecture. Okay. So here is some of the pseudocode for it. So the first thing we do is we have to choose a pivot. Then we're going to split around the pivot, the smaller half and the larger half, and then we return adding them together. So it looks pretty similar to merge sort and pseudocode. There we go. Great. Recombine. So let's talk about some of the runtimes. Now, whereas merge sort, we were guaranteed to have exactly 1/2 and 1/2 of equal size. Now, it's not necessarily based on the size of list, but based on what comes before or after the pivot. And so in that context, picking a good pivot really makes a big difference in how we divide n, how we divide in the divide and conquer stage. So can anyone tell me what is the, pardon me, what is the worst case scenario for a pivot? Yeah, sure. Oh, yes. I love how you've already jumped ahead there. You're absolutely correct. Now, n squared is the worst case runtime, absolutely correct. And that is going to be generated by what is the worst possible pivot? What's the pivot that's going to do the least amount of dividing when we're picking these things? Yeah, sure. When the pivot is the largest value. So if the pivot is the largest value or related the smallest value, then it's going to do essentially no division. It's like it just shaves a single item off, and a list of just n minus 1 goes to the after pivot, and then just one item goes to the before pivot, or no items go to the before pivot. So it's like we're barely dividing it. And like our friend suggested there, if we write out the recursion then, instead of getting that n over 2, we get the n minus 1 runtime. And if I do the math, that gets us to an n squared runtime. So unfortunately, quicksort could have a bad situation. We could have an n squared runtime if the pivot is no good. Okay, then instead, on the other side, if the worst case pivot is the smallest value or the largest value, what is the best case pivot? Yeah, sure. The median value, because that's going to split right down the middle. We're going to do the best sort of load balancing across the two recursions. And the reason that's going to give us the n log n runtime, which is the best we can do in any comparison sort, is because, remember, the number of levels of the recursion is what dictates the runtime. How many recursive calls do we need to make is essentially the equivalent of how many iterations in a loop. That's what's really the driver of the runtime. And so if we split the list perfectly in half at each level of recursion, that's going to cause us to have the smallest number of recursion. If we only do n minus 1, we have to recurse a lot to get down to a list of size 1, right? So the best case for quicksort is n log n. The worst case is n squared. And in this particular attempt at picking a pivot where we just use the thing that is in at index 0, it might seem like it's pretty likely that we could have the worst case scenario, but I'm just going to tell you, in practice, people assume quicksort has an n log n runtime. There's a lot of math to get there. It's all that amortized analysis stuff with the statistical likelihood, blah, blah, blah. But actually, quicksort is aptly named because, in fact, in practice, it does pretty reliably run an n log n runtime and sometimes even faster. It's all based on how you pick the pivot, which is what we're going to talk about in the next few slides. But before we get there, can anyone tell me, do we think this is a stable sort or an unstable sort? This was a little tough. Remember, stability is about if you have duplicates, do they remain in the same relative order as when they were first added into the unsorted list? I'm going to bail you all out. This is not a stable sort, and that's because we're sort of doing this like rotation around the pivot. And so we kind of have that same swapping nature that we have from selection sort. And whenever we have the swaps, it's unpredictable as to where things are going to go in relation to one another. So we do not consider quicksort to be a stable sort. Merge sort is stable, quick is not. Now, the way that I have shown you quicksort as of right now, is that an in-place sort or not? Anyone? Anyone want to guess? Yeah. So I've shown it to you, and it looks a lot like merge sort, right? Where we have to make new arrays that hold the subdivision of things, but there is a way that we can do it in place. I haven't shown it to you yet. So far, what I've shown you doesn't look like an in-place sort, but there's some very clever ways where we can swap all within an array. So quicksort is very popular, and in fact, it is what Java uses to sort primitives. It actually uses something called timsort, which is like this complex combination of things. Like I think it uses insertion sort if you have primitives up to size 48, and then after size 48, it does quicksort and all these kinds of things. But if somebody generally asks you what is the quickest comparison sort, the real answer is quicksort. Now, it technically has that worst case scenario of n squared, but we try to forget about it. That's why quicksort's the Beyonce. We all try to forget that she's bad at acting. Doesn't matter, okay? She's the best performer in the world. That's all we remember, right? Nobody cares about that n squared runtime. So, how do we avoid hitting the worst case? This is, again, sort of like hashing, where we're going to hedge our bets in a way to make it more statistically unlikely that we could hit that worst case scenario. And so what we need to do is we want to find a way where we are likely to find the ideal pivot, like our friend mentioned, which is the median value. But we don't want to spend a lot of computation time to find that median value. Obviously, if we looped over the entire collection and calculated the median and then split things into two perfect halves each time, that would give us the least amount of recursion levels, but we're spending all of that computation time to figure out what the median value is. Just like with the hash codes, you want a hash code that's deterministic and you need all that stuff, but you don't want to spend too much computation time to get there, so we need to find a balance. So here are a few very real ways that people have implemented choosing a pivot in quicksort. So 1, just take the first element, super fast. Don't look at anything, but probably the most likely to produce that n squared runtime. Take the median of the full array. Cool, well that's going to have us the least recursion levels, but the constant factors make it awful, and so actually no one implements quicksort technically by finding the actual median. These are two very real ones. One is take the median of 3 selective values within the array. And we are going to look at the first, the last, and the middle elements. Not values, elements. So we're going to look at the thing at index 0, we're going to look at the thing at size -1, and we're going to look at the thing at size over 2, and then we're going to take the median value of those 3 numbers. Now, if your array is just randomly sorted, then those will just be 3 random numbers. But what's nice about this too is, frankly, you probably don't come into totally random data that often. It's actually a little more statistically likely that you have some amount of order, maybe it's a little out of order. And so if your thing is kind of close to a sorted order, this is actually super effective, because then maybe small values are near the front, large values are near the back, and a median value is near the middle kind of thing. The other thing you could do is literally just pick a random element. That is also a very common thing. Computers have fast random number generators. That's also a common implementation. But the median of the first, last, and middle is probably the most commonly used approach to quicksort. So how does that work? And also, let's talk about this fancy in-place approach. So the first thing I'm going to do is I'm going to look at my 3 values, the thing at index 0, the thing at the very end, and the thing in the middle. So I have the values 8, 0, and 6. 6 is the median value of those 3 numbers. I'm going to move 6 by swapping it to index 0. And then I am going to loop from index 1 and the last index towards each other and move things out of the way so that everything before I sort of end comes before the pivot and everything afterwards. So you can see 1 comes after the pivot, we leave it. 8 comes after the pivot, we leave it. 4 comes right, we leave it. 9 comes after the pivot, and 2 comes before it, so we will swap those values. And we will continue swapping values until we get to a point where now you can see the sort of dark green is considered the low values, and the middle green is called the high values. And those are things we'll track with other variables that tell us where in the indices of the array we're navigating. But the way that we move things out of the way is with that swapping nature, and that's why quicksort is not stable, because we're going to be swapping things. Then we would repeat this procedure for each of these subarrays, where we would then look at index 1, index, 1, 2, 3, 4, 5, 6. We would look at index 1, index 3, and index 6, get the median of those, put the median there, so on and so forth. So we can do this in place, which is really convenient. Great. And then we know where the pivots are, we swap them back into the middle. And we repeat until we have a sorted list. So quick sort, benefits compared to merge sort. Quick sort can be in place. It does run an n log n in practice, but especially if you're using primitives, its constant factors generally do make it faster than merge sort, because never forget that like recursion and making new arrays and copying everything over is generally pretty expensive. It doesn't change the complexity class, but we're talking about the constant coefficients in this context. So that's why Java will use quick sort for primitives. It will use merge sort for objects. I think if you Google it, I think I put the list on here of what Java uses for like arrays.sort. And it's like if you have primitives up to the number 48, it uses insertion sort. If you have primitives more than 48, it uses quick sort. And if you have objects, it uses merge sort. Questions on quick sort before we move into some new sorting algorithms? Okay. Okay, I also told you there's another category of sorting algorithms. What if we use a structure that we've already learned? Welcome to heap sort. So if you remember, I taught you something called Floyd's build heap. That's that algorithm where instead of just like adding items individually into the heap and letting them percolate down, what if you just add absolutely everything all at once and then you call percolate down starting at the bottom level and then the levels up and up? And then I think I did some really fast hand-wavy statistical analysis, and it runs in linear time. So it takes linear time to insert a whole collection of values into heap sort. And then if you just call remove min n times, well, that will give you a sorted order. And remember, remove min runs in log n time. So heap sort can actually give us a worst case scenario of n log n, but a best case runtime of linear. Because it takes linear to put it into the heap, and if you remove min and all you have to do is swap something and you don't have to do any percolations, we could get even better than quicksort, technically a linear runtime. It is not considered stable though. It is considered n log n in practice. And can it be in place? If we get clever. So here is an in-place heap sort. The item at index 0, remember, is the minimum value. We swap that minimum value out. We start to grow the sorted areas, and then we percolate down 22. We remove min, so on and so forth. So we can just swap things around in the array just like we did with quicksort to do an in-place heap sort. Now the thing that's a little funky is if you notice, this eventually kind of gives us a reverse sorted order. So if you want it to be in the order that you actually want to run this on a max heap, or you're going to have to reverse the array when you're finally done with it. There we go. Great. Questions about in-place heap sort? Yeah?
How is heap sort different from...
That's a good question. How is heap sort different from selection sort? So it's got the same idea of like we're selecting the minimum value, but the way that we sort of order things after we do that, instead of just swapping the minimum value with selection sort, we will do the percolations, and the percolations run in log n time, whereas selection sort takes linear time to find where the next smallest value is. So we get a speed up because of the heap structure, so that the time to repair or find where this next smallest item is to do those percolations, that's a log n runtime instead of a linear runtime. Yeah, sure.
The heap sort would maintain the invariance of the heap data structure?
Yes, exactly. So like when you all implemented a heap, it probably looked a little like this, right? It was in an array. And so we are still maintaining a heap, this tree-like structure of a heap theoretically. It's just stored in an array, just like you did for P3. But what's happening is the heap is going to shrink. And so you can see here, this is kind of in green, and then we have the sorted items. It's sort of like instead of like tossing things out, we're using that space at the back of the array that's normally sort of like deleted items, because you know how when you reduce size, you just sort of don't care what's hanging out at the back of the array? This is being clever and saying, well, instead of that just sort of being the garbage bin or whatever, we're going to remove min out of the heap, reduce the size of the heap, and then place that item into the new sorted list at the space that we just made for ourselves at the back of the heap. So instead of not caring about what's at the back, that's going to be our eventual answer. Yes, please.
Wait, does the original list, does that also have to have the heap in there?
Yes, so the original list, what would happen is you would take in all of your values, and then you're going to run Floyd's build heap. And so that is what's going to take just the random sorted number of values and turn it into that heap structure with all the heap invariants. And then once you've run Floyd's build heap, which runs in linear time, then you remove min, and each of those removed mins runs in log n time. So that's how you get the n log n runtime. So heap sort, especially because it's in place, especially because it's got that n log n runtime, is a pretty popular one, especially useful maybe in interviews, things like that. Any other questions about heap sort? Build a heap with an array. Use Floyd's build heap to put everything in there, and then just remove min n times. Great. Okay, perfect. Then, okay, let's talk about two other types of sorts that are pretty distinctly different than what we've learned up to this point in time. So, when I asked you to sort exam papers, a lot of people said, well, let's make like 26 different piles based on each of the letters. That's essentially something we call bucket sort. So let's say if I give you a collection of values that are all known to be in the range of 1 to k, and we're going to start with the ideal type of data to sort. We're going to start with ints. Let's say I give you this collection of ints, and they are all in the range of 1 to 5, and I ask you to sort it. Well, what we could do is we can make an array with the same number of buckets representing the range, and instead of storing the values, we're going to store the counts. So what I would do is I would know this has a range of 1 to k. I'll make an array of size k, which in this case is 5, and every time I see a value, I'm like 5, count 1 up in this element. 1, count 1 up in this element, so on and so forth. So the way that this array reads now is that there are 3 1s. There's 1, 2. There's 2 3s. There's 4 4s, and 3 5s. So then, to produce a sorted order, I just loop back over this array and print out 3 1s at the beginning. And then I print out 1 2, and then 2 3s, and so on and so forth. So I can just reproduce those values by looping over my buckets in the inherent sorted order. And that's the key to this bucket sort. Bucket sort in this context is relying on the fact that ints have an inherent sorted order that's just going to match the way that an array would work anyway. So I'm just doing counts, and then I'm just looping over the buckets and producing that number of ints based on the value stored in the bucket. Questions on how this sort works? What do we think the runtime is of this? Does anyone want to guess what we think the runtime is? What's the runtime to go from list to buckets? Yeah, linear. I'm just looping over at one time, counting things up. What is the runtime to loop over the buckets and produce the final sorted list? Yeah, also linear. Really convenient. Now, it is linear. But to be annoying and mathy, there are technically 2 variables floating around in here. We will consider the total runtime to technically be k plus n. Now, in this particular one, I agree that this step is linear because k is obviously bounded by n. There's obviously more numbers here than there are 5. There's more than 5 values here. But it depends on the situation, right? Like maybe you have a range of buckets that's much wider than the number of values you store. And then you would have to loop over. Like let's say I just gave you the numbers 2 and 1,002 and asked you to sort them, you'd have to make an array of size 1,002 and then loop over that array to fill up those buckets. And that would be a situation where K is much larger than N. So K would bound N. So it depends on your situation, but to be the most mathematically precise, we'll say that this has a K plus N runtime, and based on your scenario, you might be able to say, oh, well, one bounds the other, where K just represents the number of buckets. Yeah? Can we use a hash map? What a great question. Let's talk about how to do this with more complicated data. So that worked with ints, right? And ints seem to fit really well into an array because indices of the array are ints themselves. But what if instead we had slightly more complicated data, like doubles? The indices of an array aren't exactly a double. And actually you can do bucket sort with any type of data as long as you figure out how to quickly produce a bucket that represents them. So we can do a hash map. And what we would maybe do is, in this case, we're going to decide the bucket is based on the, I think this is the tens digit. Am I right about this? The ones place? Yeah, thank you. The tens decimal place. And so we'll put everything that has a 1 in the tens decimal place here, everything that has a 2 in the tens decimal place here, 3, so on and so forth. And then what we have to do is within each of these buckets, we are going to have to call insertion sort. So this is a little bit more similar to the exam papers where we have 26 piles of each of the names, and then maybe you'd have to go to the stack of everybody whose name starts with an A, and then you have to sort all the A's, and then you go to the stack with all the B's, and you sort all the B's, and then you mash those stacks together. That is like the fullest expression of bucket sort. So you can technically do bucket sort with any type of object. You just have to find a way to sort of represent mapping it to buckets, very similar to a hash map, some type of deterministic way to tell you where into the bucket it goes. So some quick way to put everything into buckets. Then you sort within the buckets. We're going to use insertion sort to sort within the buckets. And then you loop over the buckets from top to bottom, and you produce the final sorted list. Questions on how this algorithm works? Yeah. I'm sorry, say that one more time. Yes, and for keys in a hash map, there's no ordering. So it's got sort of hashing-like properties, but is not technically a hash map. It's buckets, yes. So you would use an array, really. The same principle. So looping over your data and dumping it into buckets should take linear time. But then we have to run insertion sort on each of the buckets, which is technically a worst case scenario of K plus N squared, but a best case scenario of K, because remember the thing that's great about insertion sort is that it has a best case scenario of linear. Insertion sort's the one where if your thing's already sorted, it just loops over it one time and does nothing. That's why we're going to use insertion sort for the sub-bucket sorting, because this could give us a best case scenario of O of K, where all the buckets just naturally are already in sorted order. And because we're sort of assuming that the buckets are pretty small, the chances that they're close to sorted is pretty high. So there's two types of bucket sorts we've talked about here. There's the one for ints that leverages the fact that array indices are themselves ints, and it actually has a worst case runtime of O of K plus N. So this is our fastest sort that we've met so far, because it has a worst case scenario of linear. Wild. But that's only for ints. For data that is not ints, where we have to use insertion sort, it does have a worst case scenario of N squared because of those insertion sorts within the buckets. But it does have a best case scenario of linear. And obviously we cannot do any physically better than a linear runtime on any type of sort. We have to look at everything in it. So bucket sort is mathematically the best we can do. Now, in practice runtime, we do kind of generally consider bucket sort to have a linear runtime as long as k is about the same size as n. If k is much, much larger than n, then we get into some weird territory. So if you have values within a set range that you know, and those values are ints, use bucket sort. This can be a stable sort because we use insertion sort, and insertion sort is a stable sort. It is definitely not in place, though. We've got to make those extra arrays, move everything around in those buckets. It's not bucket sort without the buckets, and the buckets are extra memory. So when k is smaller or about the size of n, and there's not many duplicates, but like I mentioned, like what if I gave you 2 values that had a wide range? You'd have to make an array that's massive, that would have very few items in it. Bucket sort is a really bad choice if you have a wide range of values or if k is much, much larger than n. Questions about bucket sort? Okay, I have one more sort for you. We're going to get through it. It's amazing. Okay, final sort, radix sort. Okay, this is not a comparison sort. Radix sort only works on values that have an inherent ordering that do not require a compare to method. That means ints, doubles, strings, characters, things like that. Those have an inherent sorted order. The computer doesn't have to call compare to do it. It's called a niche sort. So, okay, yeah, you can read all that stuff. Here's the way it works. I'm going to look at a set of integers, and I am going to bucket them, but I am going to bucket them based on individual places within the value. So here I bucket based on the ones place. So 721 goes in the bucket of 1. 3 and 143 go in the bucket of 3. Then I loop over the buckets and print them out in that order. But I'm not sorted yet. I've just sorted based on the ones place. So I repeat for the tens place. So 3 and 9 go into the bucket of 0, because I sort of imagine a 0 there. 721 goes into bucket 2, because 2 is in its tens place, so on and so forth. And then I print it out. And you can see I'm kind of getting closer and closer to sorted order. And now, because my largest value in this collection has 3 digits, I do it a third time. And then I end up with a finally sorted list. So it's like running bucket sort on each of the individual digits within an integer, starting from the ones place and working up towards the higher order values. Can anybody tell me what is the worst case runtime of this algorithm? It's like running bucket sort sequentially. What's the worst case runtime of bucket sort? Linear. I just said it. I swear I'm not trying to trick you. If bucket sort's worst case scenario is linear, and we're just running sequential bucket sorts, what's the worst case scenario? This one. O of n. Absolutely. It's all just a bunch of linear runtimes. We just do one after the other. So radix sort runs in linear runtime. Boom, boom, boom. That's so nice. So if you have ints, especially large ints, meaning you probably have a wide range of k because you have very high int values and you don't want to run bucket sort, this is an optimization on bucket sort that is especially well suited to ints with a large range or a large k. And it's got a best and worst case runtime of linear. Very convenient. Any questions about radix sort? That's it. Those are all the sorts that I'm going to teach you. Like I said, there's a million other sorts out there. They're fun. You can watch YouTubes. That also officially ends the list of materials that are going to be on the exam for next Friday. Please come on Monday. We're going to talk about something called dynamic programming. Okay. Have a good weekend, everyone.